Baby's first differential equation. Suppose the year is 2020 and we are a team of epidemiologists who want to create a mathematical model that can forecast the spread of a new viral disease throughout the population. So there are like government agencies like the NIH or whatever, CDC, probably CDC, that hire mathematicians to do this kind of thing. The goal being you want to know in every city and every region how many people are going to come down with COVID-19 at what time, so that you can kind of forecast like the demand for hospital beds, right? And when should you put in place some kind of restrictions on restaurants and bars and wearing masks and that sort of thing, because you don't want hospitals to be overcrowded. So this is the goal. You can do this kind of thing if you have an accurate enough math model. And we're not going to make a math model to the level of accuracy that they use in professional life, but I want to make a model that can kind of illustrate the usefulness of differential equations. So we're going to assume that every single time that an infected individual interacts with a healthy individual, there's going to be some probability that they're going to pass the virus, and that the healthy individual is going to become an infected individual. And there's going to be some average rate that these interactions take place. That's kind of a big simplifying assumption because not everybody interacts with people at the same rate. You know, if you're a salesman, you probably have a lot of interactions every day, but you know, some people might stay in their basement all day and not have any interactions. So these are our simplifying assumptions, right? And exercise 1 says, write a differential equation that describes this scenario. So our equation is allowed to have a derivative in it. And I want to create a model. This skill is called math modeling. How do I describe a real life situation with mathematics? And this is what I would write for exercise 1. I would say that t is time, and y is going to be the number of infected individuals. So that the derivative dy dt would be a rate of change. I tell all my Calculus 1 students like 1,000 times in their first semester that a derivative is a rate of change. This is the rate of change of infected individuals with respect to time. So how quickly are people becoming infected? And so we wanted to describe the rate at which people are becoming infected. How quickly are healthy people becoming infected? Well, it's going to be proportional to the number of infected individuals. If you think about that, if you've got one infected person walking around, then the rate of new infections is going to go pretty slowly. But if half the population is infected and they're walking around interacting with the healthy people, the rate of new infections is going to go up really fast. So this rate is going to be proportional to the number of infected individuals. It's also going to be proportional to the rate at which they are interacting with each other. And it's also going to be proportional to whatever the probability is that the virus gets spread during one of these interactions. So for every person walking around infected, they are going to interact with our people every day, and every interaction is going to have a probability p of spreading the disease. And that's equal to dy dt, the number of people per day that are getting the new infection. So there's still one thing missing from this differential equation. I'll ask you a question. If the entire population was infected already, every single person already has the virus, how many new cases could we create in the following day? 0. Only this, this equation right here, if I said I have a population of 300 million people, then if y is equal to 300 million, this is still going to give me a non-zero number, right? So I need to find a way to make it so that when the entire population is infected, there's 0 new cases. And if you want to extend this argument, really to make a new infection, you don't just need an infected person, you need an infected person interacting with a healthy person. So really, the rate at which you're creating new infections is going to be also proportional to the number of healthy people we have. And for the number of healthy people, we should take the total population minus the number infected. And so that would be the number of healthy individuals. Because if we make it a little bit less extreme, maybe the entire population isn't infected, but what if 95% of the population is infected? If 95% of the population was walking around with a disease, then most of their interactions is going to be with each other. And if 2 infected people interact with each other, they're not going to spread the disease. They're not going to create a new case. And so really, the fastest rate at which the disease is spreading would be when what percentage is infected? Half. Yeah, a half times a half would give you 0.25, and that's the maximum you can get from like y times p minus y. Because if more than half is infected, then too many interactions are happening between infected and infected people. And if less than half is infected, then more interactions are happening between 2 healthy people, which doesn't spread the disease either. So anyways, this is the best we can do. For today, all we're going to say is that the rate at which new infections are occurring is going to be proportional to the number of infected people and the number of healthy people and the rate at which they're interacting and the probability that an interaction creates a new case. So that's supposed to be a lowercase p probability, and this is supposed to be a capital P population. Another thing we could do is just combine these, since these are just both constants. I would prefer to just rewrite this as like something like dy dt equals k times y times p minus y. Where now that capital P is population. And k is just a constant that represents both the number of interactions that happen on average and the average probability that an interaction will create a new infection. An interaction between a healthy person and an infected person. Okay, so this is our differential equation. This is what I would say is the answer to exercise 1. Does that make sense to everybody? So now we just need to solve this equation for y, and we will do that here in a minute. But maybe before we even solve it, we'll also just talk a little bit about other things we can learn just from looking at the diffeq. Like exercise 2 says, for the ODE described in exercise 1, I'll go ahead and write that down again. Draw the phase line and label the equilibrium points. So here's what I mean by phase line. This number line represents my variable y. And we're going to mark a few interesting points, like maybe y equals 0 and y equals p along my number line. So like normal, positive numbers are on the right, negative numbers are on the left. And if y falls in here, that means like 0 is less than y is less than p. Is y going to be increasing over time or decreasing over time? If my y variable was in this region, is it going to move to the right as time increases, or is it going to move to the left as time increases?
Is P the probability or the total population?
P is total population here. Yeah, that probability we were discussing, that got eaten up by our new constant k. Yeah. So it's supposed to be a capital P. Anyways, if y falls in this region on my number line, is the y going to move to the right over time, or is it going to move to the left over time? Who says left? Alex?
No.
No?
I had to think about my direction for a second. There's so many objectives.
Okay, who says right? 2?
Over time, it's going to get more and more of the population, right?
Yeah.
Is that what you're saying?
So over time, if my y value falls in this region, it's going to move to the right. Because remember, dy dt is the change in y with respect to time. And if y is greater than 0 but less than p, well, k is a positive constant, y is positive, p minus y would also be positive in this region. And so this is a positive derivative with respect to time, so we're going to be increasing with respect to time, so we're going to move to the right on our number line over time. What if my y falls in this region, where y is less than 0? Over here, am I going to be moving to the right over time, or am I going to be moving to the left? I heard 2 lefts. What do you think, Garrett?
Left. You're saying there's no negative, or there's no infected at all. So.
Yeah, you're still thinking about like the physical reality of like what would it even mean to have like negative people infected. I'm really just thinking about this equation right now. If y is less than 0, then positive constant times a negative number times, well, this would be a positive number in the parentheses, right? So this would be negative, the derivative is negative, so dy dt, that's negative. It's a negative change in y over time, so it's going to be moving to the left on my number line. And then just for kicks, because again, this also wouldn't really be part of the physical solution to our problem, but just out of curiosity, what would happen if y is greater? That means you have more infected individuals than the total population, right? Does my differential equation tell me that y is moving to the right over time or moving to the left over time? Left. Yeah, because if y is greater than p, k is positive, y is positive, but p minus y is negative, which gives me a negative derivative, dy dt. And so we are moving to the left over time. Okay, now what happens right here at this point where y is equal to 0? That would be a place where dy dt is equal to
KP.
0. What about right here where y is equal to p? That's a place where dy dt is equal to 0. These are called equilibrium points. And I should have said this earlier out loud, but the reason I had drawn my phase line like this, where I labeled where the 0 was and I labeled where the p was, is because I already knew these were equilibrium points in my head. But if you didn't know that these were equilibrium points, what you would do to find them is you go back to your differential equation, you just set dy dt equal to 0. And if you set dy dt equal to 0, now I can solve the equation 0 equals k times y times p minus y for the values of y, and that gives you your equilibrium points. But this is the definition of equilibrium point. If the dy dt is equal to 0, you're at an equilibrium point. We would call this one a stable equilibrium point, and we would call this one an unstable equilibrium point. The reason is because a small perturbation would cause the solution or the trajectory to diverge away. And this is called stable because a small perturbation would converge back to the equilibrium point. So you imagine, what if instead of starting exactly at y equals 0, we started at y equals 1? It's only a very small perturbation, but just the 1 means you get into this regime where we grow over time, and that trajectory is going to the right. Or what if instead of starting at 0, I start at negative 0.0001? It's a tiny perturbation to the left. Well, even though I'm barely off the equilibrium point, I'm still going to go to the left over time. And that's not a physical solution, but this is the idea. And at my stable equilibrium point, even if I have a small perturbation to the left or to the right, well, the trajectories are still pointing in towards the equilibrium point, and so it's going to converge over time instead of diverge. So that's the definition of stable and unstable. Questions yet? Okay. For the ODE described in exercise 1, plot the slope field on desmos.com and discuss initial conditions, approximate trajectories, and end behavior. Okay. Slope field. So let me open up Desmos and see if I can find out how to do a slope field. Our differential equation was dy dt equals k times y times p minus y. So I have this constant p that represents what the population, the total population would be, right? And let's throw in the k2. This is called a slope field. Later this week I'll put some slope fields on your homework, but the way it works is this. Your horizontal axis is the time axis. Maybe I should go in here and label it. Your horizontal axis is the time axis, so time increases as you go from left to right. Your vertical axis is the y-axis, that's the number of people infected. And you start anywhere, okay? Like you pick a point, let's say right here, and ask yourself what's going to happen over time. Well, as I go to the right, I have to follow the direction of these little slope lines. So as I'm going to the right and time is increasing, I'm also increasing the number of infected persons, right? Following these slope lines. And they get steeper near a halfway point where we get half of the population, and they get more gradually, gentler sloped as I get closer to the entire population. But this is called a slope field. When it says discuss initial conditions, what is an initial condition? An initial condition is where you say, right here is where I'm going to start, and this is the point where I have some initial time value and some initial number infected. These are called initial conditions. And if I start right here at this specific time with this specific number infected, I can kind of guess, based on what these lines look like, what's going to happen. And this is called the trajectory. Oops. If I choose different initial conditions, exactly the same ODE, right? But if I choose to have this starting time and this initial number of people infected, my trajectory is going to be a different trajectory. I'm going to have a different solution, even though it's still the same differential equation. And again, if I were to pick this one right here as my initial time, initial number infected, initial conditions, then my trajectory would look way different, actually. So the ODE itself is just represented by these little blue line segments in my slope field. But really, to get your final solution, your trajectory, what's going to happen in the future, what's the prediction, you need not only the ODE, but you also need a set of initial conditions. It's kind of like we're talking about Maxwell's equations, which tell you how charged particles are going to behave in a magnetic field, right? But even though that is it, that's the way that charged particles behave in a magnetic field, you also need to know where the heck are the charged particles starting, How many charged particles do you have in order to say anything about what's going to happen or what your predictions are going to be? So that's kind of the idea of initial conditions. End behavior means what happens when t approaches infinity. And so the end behavior is, let's say, if the initial number infected is between 0 and the full population, then y approaches p as t approaches infinity. If the initial number infected is greater than the number of people in the whole population, well, then y approaches p as t approaches infinity. And if the initial number infected is less than 0, then y approaches negative infinity as t approaches infinity. All right, so let's finally get down to solving this thing, because we've done everything we can except for solve this ODE. Exercise 4, solve the ODE described in exercise 1. Let me write down the ODE again. Then plot the solutions to the ODE and IVP on Desmos.com. Cool. How do we solve this? Any ideas? Just kidding. We're going to divide both sides by y and divide both sides by p minus y. And we'll see what we get. So on the left side, I'm going to write down 1 divided by y times p minus y. dy dt equals k. Everybody's good? Okay, next step. We are going to take an antiderivative of both sides with respect to t. On the right side, what's the antiderivative of a constant k with respect to t? Yeah. Call it kt plus c. Call it c1. There might be another one showing up. On the left side, when I look at this, really I like using the Leibniz notation because it makes this easier to see. When I've got this ratio of change in y to change in time, and I multiply by some increment change in time, we can treat this as being the same small time step, right? No reason they can't be the same. And so we can sketch that out. Say, well, there's 1 in the numerator, 1 in the denominator. The ratio of dt to dt is 1 if we sort of require that they be the same time step. And now what I get on the left side looks like the antiderivative of 1 over y times p minus y with respect to y. Okay, do you remember from calculus 2 how you're going to solve this antiderivative? How do you do it, Connie?
Just kidding, I don't remember.
Is it one of the trig subs? No.
We have to do partial fraction decomposition to this thing. And the way partial fraction decomposition works is we say, my solution is going to look something like a constant divided by y plus a constant divided by p minus y. And you multiply both sides by y, and you multiply both sides by p minus y, and we get 1 plus 0y is equal to a times p minus y plus b times y. So that 0 is equal to negative a plus b when I equate the y's. Negative ay plus by equals 0y. And then for the constants, I get 1 equals a times p. So that tells me a must be 1 divided by p. And b must be what?
Negative 1.
It's also 1 divided by p. Cool. So I can now rewrite this as the antiderivative of 1 over capital Py plus the antiderivative of, heck, I should have just taken the p outside of this antiderivative, right? It's just a constant. So I'm going to put the 1 over p's here. There we go. So now back over here, I can do these antiderivatives. What's the antiderivative of 1 over y with respect to y? Yeah. So it's going to be 1 over p natural log of y. And then the next one is going to be 1 over p. What's the antiderivative of 1 over p minus y with respect to y?
Negative ln p minus y.
Yeah, I'm pretty sure. I'm going to double check because I'm thinking u substitution, right? You'd say u is equal to p minus y. So that means du is going to be negative dy. So that's where the negative comes from, and this is 1 over u, so it's natural log of u. But with a negative, right? I'm pretty sure that's right. So if we make that negative, then we have natural log of p minus y. And since we're taking an antiderivative, we get a little constant. But you guys probably know this. If I've got an arbitrary constant on the right side and an arbitrary constant on the left side, I could call c equals c1 minus c2. And that way I can get rid of one of those c's. And then the next step I have something like, how to write this? On the right side, we'll say kt plus c. On the left side, we've got 1 over p. And if I'm subtracting two logarithms, like I've got natural log of y minus natural log of p minus y, how do I rewrite two logarithms and combine them? How do I condense those logarithms?
Division.
Yeah. Subtracting two logarithms is the same thing as taking one logarithm where I divide on the inside, so I've got y over p minus y. It's looking good. Now, call that p kt plus c. I could write cp if I want to, but again, this is completely arbitrary, so who cares if I multiply by a p constant or not? And that's natural log of y over p minus y. And then how do I get rid of the natural log? Yeah. I'll just take the inverse function, which is to say, take e raised to the power of both sides here. So I've got e raised to the power pkt plus c equals y over p minus y. One thing that's normally done, and I guess you wouldn't have to do this, but just it's a common practice, is to say that this would be the same thing as e to the c times e to the pkt. Right? Property of exponents there. And now e to the c is just a constant raised to an arbitrary constant. That's just an arbitrary constant. It has to be positive, of course, but it's just an arbitrary positive constant. And so sometimes people just combine that into a constant, call it c, and you make the note where c is positive over here. Okay, now we're trying to solve for y. I want a solution that's explicit in terms of y. So I can say y, my number of people infected, is equal to this function of only time. The only problem is I've got two y's over here on the left, and I want one y by itself on the left. So we're going to have to do a little bit of algebra to rearrange that, you know. In the algebra, we need to do is multiply both sides by p minus y. And then, what do you think about that? Distribute c e to the pkt to both of those. And then we will add on the left side y c e to the pkt to get rid of that on the right side, and the right side just is left with p c e to the pkt. Now I can factor out the y and divide both sides by 1 plus c e to the pkt. Another thing you can do, which is not required, but you know, is you could multiply the top and bottom by this, or you could, I don't know. Yeah, you multiply the top and the bottom by something like this. Because that just makes it look a slightly bit nicer, so that you'd get, those all cancel out to 1, and then this and this cancel out to 1. And c reciprocal is just the reciprocal of an arbitrary positive constant, so it's just an arbitrary positive constant. And then I get e to the negative pkt. That's it. And this is the solution to the ODE. Notice the one thing we don't know is we don't know what this little lowercase c is. We know it has to be a positive number for it to give me realistic solutions, right? Because it was e to a constant, and e to a real number is always positive. But we don't really know what that is. We don't really know what that lowercase c is. Even though we have the solution to the ODE, we haven't yet solved what's called the initial value problem. So now let's solve the initial value problem. And hopefully the end here will be kind of rewarding. Okay, but here is the initial value problem. The initial value problem says, let t equal the initial time, and let y, the number of infected, equal the initial number of infected. And then we get that y0 is equal to p divided by 1 plus c e to the negative pkt0. And we solve for c. And we would solve for c if we multiply both sides by the denominator, distribute the y naught, and then subtract y naught from both sides. We'll see how that goes. So that way I would end up with y naught c e to the negative pkt naught is equal to, we just multiplied both sides by the denominator and then subtracted y naught from both sides. And then to solve for c, we divide by everything else. So you get c is equal to p minus y naught divided by y naught, and divided by e to the negative pkt naught. Of course, if I'm dividing by something with a negative, what I could do is multiply by e to the pkt naught. So this is the solution to my initial value problem. So I use the letters ODE because ODE stands for ordinary differential equation. That's the solution to my ordinary differential equation. And then in orange, that's the solution to my initial value problem, IVP. Questions? I think what you're going to find out this semester is that differential equations problems are not that difficult. They just take a really long time. Like, how long have we been working on this problem? 45 minutes. That's pretty typical. It's pretty typical for a question in lecture to last 45 minutes before you get to the solution. It's not going to be uncommon. That's going to be the theme this semester. So let's go back now on Desmos where my slope field is, and let's graph on top of this the solution. And the solution to my ODE was y equals p divided by 1 plus c times e to the power negative pkt. Only t in Desmos is going to be x. And then I need to know what my c is. Well, c was the solution to my initial value problem, which is p minus y0 divided by y0 times e to the power pkt0. There's one more thing I want to do, which is make a coordinate pair t0 comma y0. And let's fix the colors. Everybody sees how I did that? That's the solution to my ODE. That's the solution to my initial value problem. And then what I also have to type in Desmos is like open parentheses t0 comma y0. And that's going to put this point in red on that coordinate pair. And what I really like about Desmos in solving ODEs is I can take my initial values and quickly choose a new initial time and choose an initial number of people infected, and Desmos will automatically tell me now what the solution curve is going to look like, what the trajectory looks like. So again, in this picture, all the little blue lines represent the ODE, right? What's happening with my ODE? What is the ODE prescribing? It says, well, if you take this ODE to be the law, this is how things are going to progress with time. The red dot represents the initial conditions, and then the orange curve represents the trajectory, but the trajectory is defined by both the ODE and the initial conditions. You can see what trajectories look like for the non-physical answers, like if you've got more infected than population, that's what the trajectory looks like, or if you've got less than 0 infected. But yeah, pretty cool. Big fan of Desmos. All right, so recap vocabulary really quick. A differential equation is any equation that contains a dependent variable, which we call y, and at least one of its derivatives. So you see y or prime or y double prime or something. An ordinary differential equation involves ordinary derivatives. So there's only one variable, and usually that's lowercase t for time. Just as an example, here's a real equation that governs an electrical circuit where, like, I know R is resistance and Q is charge on a capacitor, E is potential, C is capacitance, L is like inductance in an inductor. Anyways, there's certain circuits that obey that circuitry law. But it's an ordinary differential equation because it tells you what's going to happen to the charge on the capacitor over time. A partial differential equation, or PDE, involves partial derivatives, so you end up with more than one independent variable. In this case, with the heat equation, your two independent variables are x, which represents some spatial dimension, and t, which represents time. So you end up with partial derivatives. In this class, we're only going to consider ODEs. We are not even going to consider partial differential equations. It's usually a much more difficult course, and most universities will save that for grad school. A first order ODE is a differential equation that involves only the first derivative. So first order means first derivative. The differential equation we just solved a moment ago, that was a first order ODE. If I say second order ODE, that is one that has the first and second derivatives, or maybe just the second derivative, but the idea is the greatest order derivative is 2. In an autonomous ODE, that's a new word, the independent variable t does not appear in the ODE. So what did we just do? We just solved the ODE y prime is equal to k y times p minus y. This is autonomous. Not all ODEs are autonomous, but we call it autonomous because the variable t doesn't actually show up here when I write down the ODE. It does if I write dy dt instead of y prime, but what I mean to say is, like, this is not autonomous. Most of I think even all of the equations from physics are not autonomous. Or sorry, I misspoke. All the equations from physics are autonomous, which means they're like time symmetric. The equations of physics work whether you're simulating into the future or simulating into the past. Because time doesn't actually appear in the model, and that's what we call autonomous. Most useful stuff is autonomous. A phase line is a way to visually represent the qualitative behavior of an autonomous first order ODE, like we drew a phase line earlier. An equilibrium point is a place where the derivative is equal to 0. An equilibrium point is where dy dt is equal to 0. It's stable if a small perturbation converges, and it's unstable if a small perturbation does not converge or diverges away. A slope field is like we showed on Desmos. It's a way to show you what the qualitative behavior is of an ODE. An initial value problem is an ODE coupled with an initial condition. And so you see the solutions to the initial values are trajectories that start at the initial value point. And in behavior is what happens as t approaches infinity. The next thing we're going to work on together here is what we call verifying solutions. Which means for this type of problem, I don't expect you to sit down and solve the ODE by hand. A lot of times it's faster and easier to just plug in possible solutions, right? And if I'm giving you a multiple choice question, I'm giving you the possible solutions. So how do I plug these in and try? I would say, well, for A, I'm going to write t times y prime. What's y prime if I look at solution A?
2e 2t.
Yeah, 2 times e to the 2t minus y, which is e to the 2t, equals t squared. Is that true or false? False. Yeah, the left side of the equation is not identical to the right side of the equation for all values t, and that means it's false. The next thing we try, maybe choice B. And for choice B, write down the ordinary differential equation, but what is y prime this time? Mm-hmm. Is that true? When I look in green, is the left side of that equation really equivalent to the right side? No. So it's not B. What about C? What is y prime if I look at answer choice C?
3 plus 2t.
Okay. Is that true? True or false? Yeah, so you'll get maybe 1, 2, 3 of these test questions on your first test, and you don't have to solve the ODE. You just plug in the answer choice, see if it works. Make sense? All right. Here's another one you can practice. Consider answer choice A. For answer choice A, y is t over 3 y prime is 1/3. Y double prime is 0. And so where I see y triple prime and y quadruple prime, those are also just 0. So is it true that 3 times t over 3 is equal to t? True. So that's one solution. B looks like it's going to be a huge pain to work out the veracity of solution B. So y is sine of t squared. Y prime would then be what?
Cosine of t squared times 2t.
Nice. And when I get to y double prime, I have to use the product rule and the chain rule here. So it's like this derivative times 2t. So it's like 2t times negative sine of t squared times 2t. Plus the derivative of 2t, which is 2, times this cosine of t squared. And I'm going to go ahead and stop here. Why should I stop here?
Because it won't cancel out.
Yeah, because y prime, y double prime, y triple prime, y quadruple prime will always have sine or cosine as coefficients, right? So if I take a linear combination of like y quadruple prime plus 4, y triple prime plus 3y, it can't ever be equal to just t, because it's always going to have like sines and cosines and stuff. They're either going to cancel each other out completely to 0, or they're not going to cancel, and then I'll have something with sine and cosine as coefficients. So I can give up on B without having to put in too much time and effort there. C, let's look at C now. Y is e to the negative t plus t over 3. Y prime is what?
Negative e is negative t plus a third.
Y double prime?
E to the negative t.
Y triple prime?
Negative e negative t.
And y quadruple prime?
E to the negative t.
Okay, so is this differential equation true? It would be e to the negative t plus 4 negative e to the negative t plus 3 e to the negative t plus t over 3 equals t. Yes. So this has choices A and C. as solutions. All right. You guys try this one. Okay, I got C. Is that what y'all got?
I thought C doesn't work still.
You don't think C works?
I got C to work.
Oh. Wouldn't you be adding E?
Oh, you're right. C doesn't work. You're right. My bad. I jumped the gun. I was thinking about adding them. I was like, yeah, they've got opposite signs. They should cancel out. No, you're right. Since we're subtracting, they don't work. It is D. Okay. Now, I also mentioned this last time. This is a math class, so I'm not going to talk a lot about like application problems. I might try to work in a few like real life kind of application problems where we have a chance to later in the semester. But the way that university is supposed to work is like you learn how to do the math in math class and then you learn how to apply it in your applications classes. But like I've taken a few of these classes whenever I was in college. And I distinctly remember differential equations appearing in fluid mechanics and thermodynamics and heat transfer. Obviously, we talked about how differential equations show up in physics, like Maxwell's equations and the Schrodinger wave equation. We just showed how like a pandemic model or, modeling how disease spreads through a population could be a really useful application of ordinary differential equations. But people also use differential equations for economic models, ecological models, like how are the populations of predators and prey going to change in an ecosystem over time. Especially with regard to like invasive species that get newly introduced to an area. That's something that people rapidly try to jump on ecological models and try to predict what's going to happen to the other species if they do or don't take appropriate action. Climate models, obviously differential equations, weather forecasts, all just differential equations. Process control, whether you're doing robotics or like chemical plants. Everything is differential equations. And I recommended these videos last time. Did anybody watch either of those videos that I was pointing to on YouTube?